Alright, so in starting my journey to do my final year project, which I currently have no idea what I'm going to do, I've ordered a bunch of kits off the Aliexpress. I paid in total, let's have a look here, $33 for all of these. And there's a bunch more. I've got another set in my office as well. And so the plan is to basically go through, build all of these kits, but also figure out how the circuit works and maybe do some like manipulation to them as well. I'm hoping that by doing that, I might learn a fair bit, you know, about the circuits themselves, the components themselves. Because if I'm honest with you, like I see a relay there, I've got no idea how to use a relay at all. And that's really bad, right? So if I'm going to be good at my final year project, I need to learn about this kind of stuff. So I'm going to try and start with the easiest ones first and work my way up. This seems like it's like a police LED light thing. So let's try this one. So hopefully, you know, by the time I've soldered all of these things together, I should be fairly good. So here's the PCB. So it just looks like obviously a bunch of red or blue LEDs whichever side. You got an IC 555 timer, which I don't really know how those work. I'd like to learn. Capacitor, resistors, VCC. So okay, you have to supply 9 to 12 volts. So you can put probably a 9-volt battery there. I don't know what that is. Q. Yeah, I don't know what that refers to. You got 2 diodes there, or 3 diodes. Yeah, and we've got the same over this side as well. All right, cool. Let's take a look at the good thing about these is they come with the schematic, which is really nice. And what I'll probably do, oops, almost lost whatever this is. What I'll probably do is I'll probably build the circuit on Multisim, which is a simulation software, and figure out how this works. So interesting. This is a nice little, really good schematic to be honest. So is that, I wonder what this is. I assume it refers to like the input things where you connect the wires. So you got VCC, ground, resistor, capacitor. See, like when I look at this, I don't know what any of this is doing. If I remember correctly, the 555 timer is used as like synchronization, like some sort of like clock synchronization thing. Doesn't help that the instructions come in all Chinese. There's all the LEDs obviously. So looks like you got a transistor switching connected to this side, and this is connected to that side. Okay, so you've got transistors that are being used as the switches. The 3 diodes on either side. I'm trying to think what they could possibly be doing. I don't know what they're doing. And then the IC, I don't know. So 555 timer, probably some sort of clock. IC, I don't know. Diodes, I don't know. Transistors, I just learned about transistors for the last like 12 weeks straight. And I don't really know what, I know that they're being used as some sort of a switch, but that's all I can really tell you. Alright, let's see what's on the back here. So we've got our components list. Really sucks that it's not in English, but is what it is. So let's just read the description. This suite adopts simulation light circuit made with any 555 and CD4017. The blue LED and the red LED flashed alternately according to the pulse. The multi-vibrator, I can't read today, sorry. The multi-vibrator composed of any 555 will have a certain frequency of oscillation. The multi-vibrator. So I assume when we're talking about multi-vibrator, we're talking about this here, right? Yeah, any 555. So I've used these in my simulations in university, but you know what I mean? Like they tell you to use it, so you use it, but I've got no idea what it's doing. Okay, so it will have a certain frequency of oscillation signal send to the CD4017. It will have a certain frequency of oscillation signal send to the CD4017 decimal counter pulse distributor in order to count. Okay, so oh my days, look at this. So my look at the pins there. That sucks. Come on, man. You know how hard it is to protect. It's not hard to protect pins, man. That's really annoying. Really annoying. Ugh. Alright, well, we'll try and fix that. Okay, so will send a certain frequency of oscillation signal sent to the CD decimal counter pulse distributor. So this is a CD4017 decimal counter pulse distributor in order to count. When the pulse is 1, 3, 5, pulses arrive at Q. Okay. So Q 0, 2, and 4. So I can see Q2, which is this transistor. There's Q1, there's Q2. I don't understand because Q0, 2, and 4 output high level intern, blue LED lights flashes 3 times. So Q0, Q2, Q4, 3 times, blue LEDs turn on. Then Q5, Q7, Q9 output high level intern, red LED flashes 3 times. Blue LED flashes again when 11, 13, and 15 pulses come, and blue and red LED flashes alternately circulatory, so as to like the alarm lamp. Alright, well, I don't know what the Q is referring to. Oh, here, okay, cool. On the, okay, got it, on the IC. So on the IC, these are what's going, got it. So let's go through that again. So Q0, Q2, and Q4. Can't really see here. So I'm gonna have to, what I'll do is I'll simulate this anyways, so that I can actually watch it happening live on the simulation. But Q0, Q2, and Q4, 0, 2, and 4. 4 is this one here. Okay, so for some reason, alright, so half the pins aren't connected. I just noticed that now. So we're only using 6 of the 12. Is it 12 pins available? So this is confusing, but you'll get it. So obviously there's not 12 on one side, right? So let's see, how many are there? 2, 4, 6, 8 on one side. So it'll be like 8 and then 4 on the other side. Okay, so Q0, 0, 2, and 4 output high, and then that will drive these here and drive this whole circuitry. Then you've got Q5, 7, and 9, which is these ones here. Those will go high, and obviously those will go low. So then these go high, and then drives this whole circuitry. Or I mean, all these LEDs. All right, I'm alright with that. I understand that. Is there anything else? So change the RP1 size. Can change the oscillation period. Obviously, the English of these things is not going to be the best, and that's fine, you know. Change the RP1 size can change the oscillation period, thus changing the LED shining speed. The whole circuit, DC, 9 volts, 12 volts can be worked. So RP1 speed. They want us to change the RP1 speed. RP1 speed. RP1 speed? Yeah, I don't know. I don't know what the RP1 speed is referring to. Oh, okay. It's gonna be this, I think. So this is where's this gonna go? This is 100k pot that goes here. Alright, so that will go there, and then changing that. So adjusting this is gonna change the speed of the flashing. Okay, cool. So red flashing light and blue flashing lights form a board separately, connected with the main board through the stamp hole. The stamp hole. Don't know, maybe they mean the diodes or the I mean, that could be an English thing, innit? Okay. Connected through the stamp hole. If you need to install to other place separately or increase the distance, you should cut off through the stamp hole, then connect with the motherboard by 2 wires. Ah, okay. That's nice. I'd like to do it. I definitely would like to do that. So when we're saying stamp hole, they're going to be referring to some part of the PCB, right? So you can see this is the main board here, and then you've got, okay, these must be the transistors here, right? These two here. Just turn it over. Yeah, okay. So those are the transistors there, which are driving the whole thing. So I assume what they're saying is cut off the lights, right? And then So you would cut at the transistor. I would definitely like to give that a go. I'm assuming it's going to be to cut off. Okay, let's see if I can show you here. I assume it's going to be to cut off this from here, like this, around here, like that, and then the same again through here, and then you would just wire, I don't know, because the transistor will be left there. And when I do that, I'm probably going to break it, unless there's another video on YouTube of someone doing it, which I don't think there will be. Sadly, I looked at some of the videos on some of these kits, and most people, they just solder it together and then turn it on, and that's it. So it's a shame because you don't really get to learn how the circuitry actually works, which I really need to learn. Please pay attention to the direction of the LED when installing, especially the direction of L11 and L12. L11 and L12. Okay, we can't, there's no L11. I think they mean LED 11, so probably referring to the diode 11. 11 and 12? I don't know. No. Probably not referring to that. I don't know. Don't know what they're referring to there. L11. Let's check on the back of here. L11, L11. Yeah, it beats me. I don't know. Okay, here we've got. Alright, so no, is that right? L12 is one of the blue LEDs and L11 is the other blue LED. So probably referring to these two LEDs up here. For some reason you got to pay special attention to those. The R2 and R3 controls the brightness of the light. You can change it appropriately. The range is between 10 and 100 ohms. Okay, that's cool. So I can change the brightness of the LEDs. I'm definitely going to do that then. The more I can do to this, the more I'm going to learn. So we've got L11 and L12. Okay, no, that's different. So R2 and R3. R2, so that's R3 and R2. Okay, so these two resistors. So they said the range is between 10 and 100 ohms, but here it's got a 10K. So I think they mean the range is between 10K and 100K. I don't know what that means there. They've also got here, note, there is no IC sockets in the kits, but obviously they have provided that. So maybe they mean if there wasn't. Look at that. That's completely. This is what you get for buying cheap though. None of this stuff is protected. Look at that. Terrible, innit? This, thankfully, this chip here is okay, but look at those pins, man. The rest of the stuff seems to be alright. Yeah, everything else is fine. Okay, so we're saying that the range of the resistors R2 and R3 need to be between 10 and 100 ohms, but I think they mean, okay, R2 and R3 here on the screen here, they've got metal film resistor R2 and R3 is 10 to 100 ohms. So they're referring to these here, which is weird why on the PCB itself it says literally 10K. But then at the same time, I think, is it possible they mean, because if you look at R5 and R4, they're 100 ohms. Okay, so let's look at the schematic. This is where the simulation would be helpful. So they're saying that R2 and R3 controls the brightness. Where are R5 and R4 in here? Is that R5 there? That looks like that's R5, and then R4 is over there. So even though they're 100 ohms, I can see how. What these are these? What's this one doing? So this side of the transistor is going to ground. This is also going to ground. Okay. So the emitters are going to ground, and then you've got going to VCC, and here, okay, also going to VCC. Fine. So R5 and R4 are both directly linked to VCC. So that actually might be the one that I need to change, which is interesting because is it possible they made a mistake? So this person here said only one side's working. The blue half does not work. So it looks like a lot of people are having problems with one half of it not working. You need to give it the full 12 volts. Only one side will work on 9 volts. Okay, yeah. Let's quickly solder this thing together then, and then we'll see if it works, especially because I've got to refix these pins to bend them up properly. And then I may have some issues with this LED 11 and LED 12, which they've said to make sure I put in the right way. Have they at least given us some sort of indicator? Yeah, so they've told us positive on each side. So where would 11 and 12 be? So you see you've got the positive of each LED there. And they've said pay special attention to LED 11 and 12. But as far as I can see, all of the pluses are on the exact same side. Yeah, they are. Okay. So I don't know what they're on about there. I'm a bit concerned with these 100 ohm resistors. Because 10k, 100 ohms. I don't know. Alright, let's get cracking. We'll get on it. Alright, so I think the first thing to do is to try and fix these pins. Because if I break them, in particular, if I break the one on the IC, right, then the whole thing's pretty much pointless, right? I mean, maybe with the IC, I think because we're not using all of the pins, maybe I might be able to get away with breaking one or two. But yeah, I mean, ideally with these, when it comes to these pins and stuff, you can get one of these like kind of machine things, not machine, but some sort of device that re-bends them for you. Just concerned not to put too much force on it. Alright, so I think that IC is okay. That will probably survive. So now with these, I don't necessarily need the holder, so it's not that much of a problem. Alright, that's kind of okay. There we go. Alright, so that's all good, thankfully. So let's get started now with the resistors and diodes. Alright, so I think probably best to do the diodes and resistors. So we get our sheet, and then the diodes, are they all the same? D1 to D6, so there's 6 of them, 3, 6, yep, and they're all the same. Alright, just in case you haven't done this before, it's fairly simple. You go with the black line on the diodes, and then attach it to where this line is on the side here. So I'll do one pretty quickly, and then I'll speed through the rest. Like I said, the soldering is probably, if you're trying to understand it, the soldering is the easiest part. So I don't recommend buying these kits if all you're going to do is just solder it, because that stuff's easy. So just like that, you got the black line on one side, and that goes down like that. So along with the same line. Alright, cool. So I'll do the same for all 6 of these, and then just solder them on. I'm rushing a bit, so it's a bit wonky. I don't know why I'm rushing. I kind of got some pain in my hand. I think it's from too much computer use. But yeah, so I'm rushing a bit. Diodes are done, so I'm gonna do the resistors now. I'm a bit concerned about, to be honest, in terms of, so there's no labeling on them, but obviously we've got 3 of the same type and 2 of the same type, and we don't have any other resistors. So let's have a look here. We've got 3 resistors, R1, R2, and R3, and then we've got, should have another 2 somewhere. Oh yeah, here, R4 and R5. So R4 and R5 are 100 ohms, and R1, R2, and R3 are 10k. So we'll do R1, R2, and R3. I can see R2, can see R3, and R1's there. Alright, so gonna do R5, R4, and R5 now, which are the 100 ohm ones. So these are the ones that I'm probably gonna need to change. I can't remember what it said in the instructions, but to adjust the brightnesses, I think. I'm not sure, so I'll probably change these later on in the video. R4 and R5. Alright, so I'm just going to do the transistors. I got 2 capacitors and then this switch. And once I've done those, then I'll do the LEDs and the IC. So assume this capacitor goes here. In case I've had this issue before, whereby if they didn't have the plus sign, this stripe sign would be the negative, but they've got a plus sign there for the capacitor, so that just goes in like that. And you got the smaller capacitor, which these ones, they're ceramic ones, they're not polarized, so you can put them in any way you like. Interestingly, I can't see where this goes. I assume it must go here. No. Okay, there. You can see it just slightly over there. See, I mean, that was dumb to say that it's gonna go straight on the input. That would have, so that goes there, like so. What I've done is, I've actually got, on my Pi Mac over here, I've just got the image of the whole thing there, so just there, when I was like, does it go there? I just looked up and I was like, no, it goes, obviously goes there. So I'll put the transistors in now as well. So I'm kind of, yeah, like I said, rushing it, and because I know that I've got a lot of soldering coming up with the LEDs, so I'm like, okay, let's do this. So I'm gonna do this potentiometer. There you go. I'm gonna put this in now, into here, and then do the ICs, and then do the LEDs last. But yeah, so the way it's currently going right now, it's all a bit like wonky, but that's fine. It will all still work. This potentiometer doesn't go all the way flat, which is, I've messed up now because the capacitor is actually taller than the pot, so I have to hold it with my finger and then solder it just using one hand like this. So if I put some solder on my tip and then just try and get something on there. There you go. Alright, so that was there, and now I can solder it. Alright, that's done. So now I'm just going to do the ICs. So we've got to put in the base for them. The only thing you've got to worry about here is just the notch. So just look for that notch there. Alright, so IC sockets in. I mentioned this in another video whereby basically I learned in uni that I shouldn't put the chips in yet until once it's fully ready to go, then connect 12 volts in, just in case if you made an issue, you don't want to kill your chip. So for example, if I then connect it and I've reverse polarized this capacitor and then it blows up, that might have killed my chip. So it's always good to leave the chips out first, connect the power in, then do it. So that's what I'm going to do. So I'm going to now solder in all these LEDs. I'm aware that I need to be careful about LED 11 and 12. I'm not sure why, but yeah, I'm just gonna go ham on it all. I don't know which side. It seems like, based on the picture I'm looking at, blue is on this side and red is on this side. So let's go put all the blue ones in and we'll do all this. So this is a bit mad. They didn't give me enough red LEDs. This is crazy. I believe I have some. I mean, I definitely have some, but yeah, so I have two LEDs here. Let's just see if they're the same size. Right, yeah, thankfully they're exactly the same. But yeah, that's a bit annoying. So just be something to be aware about, that if you buy this kit, they may not give you all the LEDs. That's funny, right? Alright, let's solder these. And then last up is just to attach these wires. So red wire to the VCC, and then blue wire to ground, and then just solder them in underneath there. That's what I'm going to do. This is a bit tricky to do. There you go. Alright. There you go. And we're done. Alright, so that's attached. What do you think? I rushed it a bit, so you can see my red LEDs are quite flat, and the blue LEDs are quite raised. Actually, I need to probably trim down most of these at the bottom here, because I'm thinking I might give this to my toddler and to play with. and it's quite spiky. All right, cool. So let's connect uh 12 volts into this, and then make sure there's no capacitors exploding or anything, and then we'll put the ICs in. All right, so the way we're going to do it is I've got my power supply here. This one is the Eventech, really good power supply actually. So we're going to turn it on, and then we're going to go 12 volts. Yeah, 9 to 12 volts. Cool. So we've got 12 volts, and then we'll put the amperage down to the current down to the lowest, just enough for it to turn on, but I don't want it to try and put out max current. So now we don't have any IC connected. So positive, negative. So this wire is a bit funny, but you can see no explosions or anything. So now let's just take this off and connect up, put in our chips, which are going to be a bit tricky because the pins are bent. So again, just the notches. Alright, cool. So let's try it again. Positive, negative. There you go. That is nice. And so apparently it's drawing 0.01 amps, so 10 or 20 milliamps of current. So let's see if I crank up the current to max. Okay, that doesn't make a difference on here. Alright, that's fine. So let's turn it on the potentiometer. Oh, that's cool. It slows down. So this is a max speed, and then all the way down to the bottom. Oh, why are those ones off? You can see that this row is off, right? I'm not missing that. Look, watch this whole row, this whole column here is off. Oh, what's happening there? I wonder, do I need to make it go faster? Would that make a difference? No. Let's just pay attention to this. Yeah. Yeah, look, so that whole column's off. Interesting. Let's put up the voltage maybe. Nah, no difference. Alright, let's turn the voltage down. Let's go to 9 volts. Yeah, so on 9 volts, the blue won't turn on. You can see that it's struggling. It's fine above 9 volts, so about 10 volts minimum you needed. Okay, so we've got to figure out why this column here isn't on. Interesting, right? So this is what I basically wanted really to happen, because I'm thinking that even maybe one of the pins on the IC is a problem, or could be a dodgy soldering job, right? Now they did say to be aware of like diode 11, diode 12, the polarity, but I can't see any difference on the schematic or on the board. So interesting. All right, so in checking my LEDs, right? So it's this one. What I'm thinking is one of these is probably reverse biased. Now, what I did notice is that you can see there that is not soldered on properly, so that might be causing an issue. So I'm just going to resolder that, take some solder off that, and put it on that, and then see if that solves the problem. I'm not sure why that would cause the problem, if I'm honest with you, because I still think it's still a kind of decent enough-ish connection, but I've only just turned my solder iron on, so it's taking a while to heat up. There you go. I mean, we've got a giant blob there. Yeah, my soldering is not the best, as you can see. So I don't know if that's gonna make a difference now. Let's run it and check, but I don't think that will. So what I'm thinking more than likely is that one of the LEDs are reverse biased. Oh, look at that. It worked. That's mad, isn't it? So it was literally just that one. Um, it was just that one bad solder joint, which is mad, right? I wonder why that is. So I assume that's because each diode is going back to the input on the IC, and so because this each one of these is in parallel, so these two worked fine anyways. But this one, since it's the third parallel, probably for this diode, that was breaking the circuit, and so maybe, for example, electricity was flowing fine here, current was flowing fine here, but it wasn't flowing here because of that bad soldering there. Interesting, right? Anyways, I'm glad it works now. So I think now one thing I obviously know is that this potentiometer, right, is obviously changing the frequency of the clock, the 555 timer. So this 555 timer, as you reduce this, then this is what's slowing down the whole circuit, since the whole circuit is ticking off of this, right? So what I'd like to do is, I think, I'm going to Google these two chips, learn about them, and I'll come back to you. And then after that, we'll do build this same circuit in a simulation, and see how that looks. Yeah, I'm quite intrigued by that, and then I'd like to play around with some of the values and see how much they think. This is actually quite bright, to be honest, on 100 ohms. So if I reduce these resistors down to 10 ohms, I mean, providing they don't blow up, it should be very bright actually. I'm very happy that that's really cool. Okay, so let's I'll get back to you guys once I've figured out what's going on with these two chips. Alright, so let's talk about what the different components of this thing do. I've done a bit of research now, and I'm very confident I fully understand the entire circuit. So we'll talk about what each component does, and then we'll jump onto the computer and do some simulations, and I'll show you some different things about how it works. It's always nice to look at the schematic and you can see the different current and voltage probes and what they're doing, which is fantastic. So briefly run through what each component does here, and then we'll jump on the simulation and take a more in-depth look at it. So first up, you've got this small IC here, which is a 555 timer, very, very famous timer. What it basically does is it produces a single rectangular pulse, right? And it does that repeatedly, and this will serve as the clock, which basically runs our whole circuit. So what we're going to get is we're going to get a pulse of voltage, and that's going to send like an output 1 to the IC to do something. Then you'll get like a pulse of no voltage, and the IC won't do anything. Then you'll get another pulse, and then the IC will do something. So it's just sending continuous rectangular pulses, just like a square wave. And basically, it's the conductor of the circuit which is telling the IC, this IC here, what to do. So that's what the 555 timer does. So this IC here is a CD4017. CD4017. So this is what they call a decade counter. It's called a decade counter because it's got 10 output pins, and obviously 10 being a decade. So what this is going to do is every time it receives a pulse from the 555 timer, it's going to send its first pin high, so Q0. It will send that pin high. Then on the next pulse, it will send Q1 high, next pulse Q2, and so on and so forth until you get to Q9. And then after that, it will repeat back down to Q0 and continue over again. So you've got these 6 diodes that you can see here. These diodes are basically just serving as reverse voltage protection for the IC. So the IC is connected through the diodes to the LEDs. And so you obviously don't want voltage coming backwards and killing off the IC. So that's what those diodes are there for. These diodes are actually the 1N4145. What's interesting is that here on the board it's got 1N4148. So I'm not entirely sure. I can't exactly read what's on it. But on the schematic that they sent me and in the description, they mentioned that it's a 1N4145. If it is the 1N4145, then these have a reverse voltage protection of 1000 volts, which is mad. So obviously you don't need 1000 volts protection on this. So next up, we've got these two transistors. Let's get a closer look at one of them. So if you can see there, you got S8050. S8050. So these are just standard NPN transistors. What these do is these serve as switches for the LED circuits. So the LEDs are always connected directly to the 12 volts, right? And then you've got 12 volts at the LEDs, and then between the ground and the LEDs are these transistors. So this is where things get a bit confusing, because basically the listing have R3, R2, and R5, R4 mixed up the wrong way around. So R3 and R2 are the resistors that control the base current of the transistor. So what the transistor does is it acts as a switch. So you can see here, these two pins are the resistor here, this one. And then, so we've got our resistor connected to our base here. And so when this resistor here receives current, and the current goes through to the base, the transistor opens its floodgates and it allows VCC to come from this side to fly through. So the 12 volts will fly through the transistor and then come to this now here LED circuit, which is all about LEDs here. And then the exact same thing on this side here. You've got VCC coming from this side. You've got our transistor here. This is our resistor here. So there, these two are resistors, and so you can see this pin here connects to the base. Then when the base is activated, it allows the current to flow from VCC here through the transistor and then to activate this whole LED circuit here. So actually, if I wanted to cut off the LEDs, for example, if I cut here and here, I'd probably want to put a jumper cable, you know, from here to there basically. So from the transistor, leg of the transistor to the LED circuit, and in here it's just going back to these are resistors going back to ground. So according to the data sheet, that these two transistors here, they can handle 1.5 amps. All right, so for the LEDs, fairly basic. They're just standard 5mm diffused LEDs. So the only thing to know, and probably importantly, the reason why the blue LEDs didn't light up on 9 volts, but the red ones did, was because the red LEDs only require 1.6 volts or up to 2 volts, whilst the blue LEDs require a minimum of 2.5 volts and, up to 3.7 volts. So the 9 volts is supplying enough voltage for the red LEDs, but it's not supplying enough for the blue LEDs. So you've obviously got this potentiometer here. So this is a 100K pot. Now what it does is it controls the frequency of this 555 timer. So adjusting this pot, what it will do is, and I'll show you this on the simulation, it will actually widen or shorten the length of the pulses that come out from this 555 timer. So for example, if you think about it, right, if you have a very short pulse, that means your circuit is flying. Your frequency is obviously very fast, very high, and so the whole circuit works much quicker off of short pulses. So on off, on off, on off, on off. So you're gonna get, for example, the 3 flashes between these rapid, basically. Whilst when you turn it the other way and then you have the pulses a lot longer, it takes a lot longer for the circuit to flash, the red LEDs 3 times than the blue LEDs. So that's where basically this controls the speed of the circuit. That's what this potentiometer does. So I've already covered R2 and R3, which basically serve as current limiting resistors to the transistor. So they're connected to the base of the transistor. So without them, you're going to get a high current going through to the base. You don't need a high current and you don't want a high current. You want a small current, so you have a nice large 10K resistor there to limit the current going to the base of the transistor. You've likewise got R1, which actually works as a current limiting resistor to the 555 timer. So again, you don't want a large amount of current going through to the 555 timer. So immediately from VCC, straight away you've got a resistor which limits the current going through to the 555 timer. So last up, you've got the 2 resistors here, which is R5 and R4. These basically, it says in the listings that they can be from anywhere from 10 ohms up to 100 ohms. So right now we've got 100 ohms in. What that's supposed to do is, obviously the larger the resistance, then it should limit the current going through to these LEDs, which should basically make them less bright. So I find them to be very, very, very bright on 100 ohms. So if you reduce that down to 10 ohms, you're probably going to get super bright LEDs. And if you reduce it down to 0 ohms, you're probably going to blow them. So yeah, just something to keep in mind. But yeah, these resistors control the brightness of the LEDs. And actually, some improvements I would make is, if I wanted to use this, I probably wouldn't need them to be that bright. So maybe to save power, especially if you're running off of a battery, you I don't know if that would work actually, but basically you could reduce, or you could increase the resistance of R4 and R5, and that would make them a lot less brighter, and I think that would save power. But maybe it might just be dissipating that across the resistors. I don't know. Don't quote me on that. All right, and then finally, the only other two things we haven't covered are these two capacitors here. So you've got C1, you can see here, and then C2, you can see there. See C1, C2, see there. Sounds weird, right? So C1 is a 10 microfarad capacitor, and C2 is a 0.01 microfarad capacitor. So what C1 does, interestingly enough, it actually charges through R1 and R2. So you've got R1 here, R2. So this C1 will be charging between these two, and then when it's charging, the output of the 555 timer will be high. So this is basically what's creating the pulse of the 555 timer. So the output of C1 will be high, and then when C1 reaches 2/3 of the supply voltage, which is 8 volts, then it will discharge through the resistor R2, creating a pulse, and then the output obviously goes low at that point. And then when the voltage across C1 drops below 1/3 now, so basically it's going to activate at 8 volts, right? And then as it starts to discharge, when the voltage of C1 drops below now 4 volts, then it will start charging again, and the output will go high again, and then the cycle will repeat itself. So this capacitor is going to constantly keep on charging, discharging, charging, discharging, and that's going to create our pulse waveform basically. So that's what this C1, very, very important capacitor. Without it, the circuit wouldn't work actually. Then for C2, it's just a very standard basic capacitor where all its job is basically to remove any noise from the circuit, in particular from the 555 timer. And that's it really. So that's all of the components. And to be honest, I'm amazed because when I built this, or didn't build it, but when I soldered it together, I didn't really understand. I didn't know what these were at all. I kind of had a rough idea kind of what a 555 timer was. I didn't know what anything was doing. I didn't even know actually that the transistor was serving as a switch. So yeah, so that was my mad ignorance. So I've enjoyed a lot researching these circuits, and basically I googled what each component did, or I googled what each component was first of all, and then googled its use cases for it, and then tried to search up online this particular circuit, 555 timer circuits, how the decade counter was used, and I've learned a bunch. Like, what I've told you here now is a summary and only really what I remember from my like studying of this. But yeah, I mean, I'm sure in my head I've probably got a lot more somewhere, just not to mind right now. All right, so let's jump onto the computer and then we will take a look at the schematic, which again I learned loads doing this, and thoroughly enjoyed it. So yeah, what we'll do is we'll jump onto the computer, go through the main schematic, talk a bit more about how the pins work and how you get to flash 3 on each side, and then I'll just go into a bit more detail about maybe like the output points of the IC and the voltage and stuff like that. So yeah, let's get into it. All right, so here's the schematic. It took a while to build on this multi-sims, but I got it in the end. So if you have a look over here, we've got the VCC 12 volts, we've got our ground. Here we've got our 555 timer, and here we've got our CD4017. Got our 6 diodes here, the resistors that connect the output of the diodes and the IC, the 4017, to the transistors. And these 2 transistors, they're driving the LEDs. So you can see here, along this top here, you've got VCC coming through these LEDs and then coming to the transistor, which then allows them to go back towards ground. Same again here, where you've got, for example, you got here, this part is all 12 volts here coming to the top of these diodes, or these LEDs, and then obviously current will come through all these LEDs and then up here and into this transistor here and then back to ground. This is the whole circuit. So let's watch it in action. I'll run the simulation. You can see here the red LEDs flash 3 times and then the blue LEDs flash 3 times. And then it repeats itself again. So the circuit's using a 555 timer and a decade counter, and the 555 timer is producing a continuous pulse at this output here. I'll show you. we're using an oscilloscope. Take a look at that. So let's stick an oscilloscope on this output here and take a look at the output of the 555 timer. All right, so here we've got an oscilloscope. As you can see here, the channel A is connected to the output of the 555 timer. Zoom in a bit. See that's connected to the output, and then ground is obviously grounded to ground, right? So let's run the simulation and then take a look at the output of the oscilloscope. You see here we're getting a nice steady pulse output. And so this is what's driving basically the whole circuit in terms of when to move. So now if you come over here to this potentiometer, you see it's currently at 40%. That's 40% of 100K, right? So if I come all the way down now to 0%, you can see that the pulses are a lot longer. And if I bring it all the way up now to 100%, you see you basically have a continuous pulse. So as I change the value of this potentiometer, you can see that the gap between the pulses, as I reduce it, gap between the pulses increases. As I increase it, the gap between the pulses decreases. That's what I mean by this potentiometer controlling the frequency of this 555 timer, meaning the distance basically between each pulse. So if you crank it up to the top, you've basically got no distance between each pulse. Put it down to the bottom and you've got a huge distance. Cool, so that's how that works. All right, so let's look at the output of the IC, because if you look here, you can see I've got 9 pins, Q0 to Q9, and I've got Q1, Q3, Q6, and Q8 blank. All right, so here I've got a voltage probe, which is basically just going to tell me the voltage at each one of these points. So it's connected to all 6 of the outputs that we're using of this 4017 decade counter, right? So when I run it, here, you're going to see this part's going to go to 5 volts, drop down. Here goes to 5 volts, drops down. Here goes to 5 volts, drops down. You get here 5 volts, drops down. Here 5 volts, drops down. Here 5 volts, drop down. And as that's happening, you'll see over here that the LEDs are lighting up red, and then you're going to blue, and this final one here. All right, so let's check the output of our oscilloscope here. Let me just show you what the oscilloscope is connected to. So the oscilloscope channel 1 here is connected to this output it's connected to the base basically of the transistor for the red LEDs, and channel B is connected to the base of the transistor for the blue LEDs. When I click it here, you're going to see that basically when one of these, right, let's zoom out a bit. Here we go. So you can see here that now channel 1, which is the red LEDs, is ticking away. Then that's going to turn off and go off. And you can see channel 1 is off now, whilst the blue LEDs are ticking away. And then you can see these spikes here. It's probably due to probably need like some sort of capacitor to smooth out the output there or something. I'm not sure why those spikes are happening. But the most important point here is that you can see here that channel 1 turns off, and then channel 2 goes, and then channel 2 is going to turn off, and channel 1 starts going. So I'd like to elaborate on that a little bit more. So let's just go in and just show you a bit more about how it works. So obviously we want each pulse, we want the each section of the LEDs, so the red LEDs and then the blue LEDs, we want them to light up 3 times, right? So this decade counter is going to send each one of its pins consecutively high. So Q1 will go high, sorry, Q0 will go high, then Q1, then Q2, then Q3, then Q4, all the way up to Q9, right? So what we want is, we don't want just a continuous pulse. So if I have Q0 here and I have Q1, both of them, if I have, for example, Q1, and then I had this second diode connected to if I had Q0 like this, right, as is, and then I had here Q2, simulation. If I had this now connected to Q1, you're just going to see high, high, and then if I had here now connected to Q3, it's going to be high, 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 right? So the output Q0 is high, then output Q1 is high, then output Q2 is high. As this transitions from one output to the other, it's not going to be enough time for you to see the LEDs flash, or it's not at least going to turn off. So we want it to turn off and then on, off, on. So the way that we do that is then by having it wired up like this. Here. And so now Q0 goes high, and then this here diode comes, the current flows through here, and then activates, comes through this resistor, activates the base current here, and then that turns all the LEDs on. Then Q1 will go high, but it's not connected to anything. That means that all of the LEDs will turn off, right? Then Q2 goes high, and the red LEDs turn back on. Then Q3 goes high, obviously Q2 going low. So Q3 goes high, it's not connected to anything, so all the LEDs turn off. Then Q4 goes high, and the red LEDs turn back on. Here's what's interesting now. Then Q5 goes high, no need to have anything off. We're just transitioning now from red to blue, so we don't want all the LEDs off. So now immediately the blue goes high, then it goes low again, blue goes low, LEDs turn off because Q6 is high now, but not connected to anything. Then Q7 goes high, blue LEDs turn back on. Then Q8 goes high, it's not connected to anything, so nothing, all the lights are off. And then Q9 goes high, and then blue LEDs turn back on. So at this point now, the red LEDs, which is Q0, Q2, and Q4, have turned on 3 times. And then the blue LEDs, Q5, Q7, and Q9, have all turned on 3 times. And then now what happens is the 555 timer continues to keep on ticking over. And then here now, this will just repeat itself back to Q0 again. That was one mouthful, but yeah, that's how it works. All right, so let's get even a little bit more into the weeds. And I really have learned a lot doing this. So yeah, I mean, I'm thoroughly enjoying this. Let's talk about this resistor R1. So if we run this simulation now, and then we put current probe onto it here, and then we'll also put one here going into the IC, the 555 timer. Okay, so what we're going to find is that obviously the current's going to fluctuate depending on whether the clock 555 timer is going high or going low. So you can see it's going in the microamp region, and then it's peaking up to the milliamp region. So what I can do is I can actually come into the settings of this simulation and slow it down a bit. So if I slow it down by a factor of 10, run it again now. Now you can see microamp, 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 and then it will jump up to milliamp. There you go, 1.2 milliamps up here, and you're getting 1.3 milliamps here going into the 555 timer. This is all thanks to this 10K resistor. So now, if I remove the 10K resistor, right, and then do the same circuit again to make this connection. Okay, go with that. So now we've got 12 volts and current is unimpeded going straight into the 555 timer. So let's see what kind of current we get going into it. Boom, look at that. 2.4 amps straight away, consistently going straight into the 555 timer. And then let me just speed up the simulation. So now we've got 2.4 amps going into the 555 timer. And I'm assuming at this point now you can see, so my simulation is running, but none of the LEDs are turning on. And that's all from just removing this 10K resistor. And I'm assuming what's happened here now is that this 555 timer is fried. So yeah, so that's why you need that 10K resistor there at R1. That's to protect and limit the current that's going into this 555 timer. So let's close this because my 555 timer is now fried. All right, so we've got our 10K resistor back there. Let's just run the simulation again. And now you can see everything's working correctly again. LEDs are lighting up. So definitely need that R1 resistor. Let's go over here and talk about R2 and R3. So like I said, they're limiting the current that's going to the base of these transistors. So let's take a look at the current. Take a current probe there and another one there. So what's happening here is that we're getting our output is coming here from our 4017 decade counter, and it's coming to the base. Now you need a certain amount of base current to activate the transistor, but you don't want too much to the point that you're just going to kill the transistor, right? So we want a small base current that's going to activate the transistor here and allow the current to flow through. So what we're seeing is that when this here, you see it's currently at its nanoamps. When it jumps up to microamps, that activates the base, that base current in the microamp region, so 356 microamps in this instance, is then activating this transistor and allowing current, the whole current of the whole circuit to fly through all of these LEDs and go to ground. So in the nanoamp region, basically you're looking at no current flowing at the base of the transistor. And the reason why you're getting nanoamps is because of the fact that these are now low. So you're getting maybe some small trickle current coming from the rest of the circuit, but it's nanoamps. It's not enough to activate the base current of this transistor. So now, like I said, these resistors here, R2 and R3, they're 10K. So they're limiting the current at these transistors. So let's remove one of them. We'll remove R2 from the circuit. Let's just connect now. So now what we're doing is we're connecting our IC through a diode, or through these 3 diodes in parallel, straight to our transistor. So let's have a look at how much current we get coming out of this IC and going straight to the transistor. Run the circuit again. Now you can see there we're getting nanoamps and then up to 2 amps. Nanoamps and then up to 2 amps. So the circuit is still working, it appears. And I'm pretty sure this transistor can only handle 1.5 amps. But in my simulation, I couldn't find the exact transistor that we're using in the actual circuit. So I'm using an ideal transistor. So maybe it's ignoring its realistic abilities. But 2 amps would probably be too much current to put through this BJT NPN transistor. So you can see here 2 amps. The purpose of these resistors here are to limit the current that's going through to these transistors. So you definitely want those resistors there, and you want them being a nice high value 10K. Perfect. And one thing I learned in my first year of electrical engineering is that if you want a current limiting resistor and you're not sure what value to put, just go with 10K. That's what I learned. So yeah, that's what I'm going to do moving forward. Stick a 10K resistor in there and hope for the best. Make sure it's not any expensive stuff. All right, and then lastly, let's just stick some voltage probes across the different LEDs, so we can just see clearly that red LEDs and blue LEDs are using 2 different voltage levels. All right, so I've put voltage probes across these resistors here. So watch as we're turning, across these LEDs. So as we're turning on these the red LEDs, you can see that we're getting a 1.8 volt drop. Obviously, we're just going to have a constant voltage drop across them. So we've got 1.4 volts, and then when it turns on, it goes up to 1.8 volts there. And so you can see down here on the blue LEDs, we've got 2.4 volts resting, and then when it turns on, it climbs up to 2.83 volts. So with no current flowing through the LEDs, we're getting, for the red, we're getting 1.4 volts, and for the blue, 2.4 volts. So the blue LEDs are using an extra volt more than the red one. So that's the reason why 9 volt doesn't work when you're trying to power the circuit, that it doesn't actually light up the blue ones. It's just not enough voltage. So I found that it works fine with 10 or 11 volts. So all right, that's it from me for the simulations. Like I said, I learned a bunch doing this. Thoroughly enjoyed it. Just making this circuit alone and finding each of the components that I needed, it was difficult, very difficult, and I thoroughly enjoyed every moment of it. So this is brilliant. Let's just jump back to the actual circuit now. All right, so I hope you enjoyed the simulations. I really enjoyed it. Now, if you're new to this channel, you probably might not know this, but me, I'm a very clumsy kind of guy, and I really do not look forward to the day that I'm working on high voltage. Bloody hell, man. So anyways, I'll tell you what reason why I said that. I basically killed this IC. Not basically, I definitely did kill it. And what's funny is I'll show you the video here, but let's see if you can see. Okay, you can't really see it, but you see all that kind of I don't know what you would call it, like grease looking thing. That's from where I killed the IC. There's not really any more signs on it, but definitely this IC is beyond dead. Basically, what happened was I reversed the voltage on this. So and obviously good circuits would have protection for that, and that's something I'm going to discuss in a minute, that maybe future improvements that I could add to this would be to add some sort of diode in here to make sure that I don't fry the whole bloody thing by reversing the voltage, because it's super easy to do, man. And I just wasn't, basically I was working on it like this, right? And so I just connected it how I normally would, and anyways, I killed the whole thing, and the magic smoke got released. So once the magic smoke's out, you can't put it back in. So anyway, so I've ordered another one of these chips, but what I also noticed was, as my power supply was still connected to the circuit, I noticed that I was getting 4 amp spikes. And so what that tells me is that something got shorted inside the IC, and it was probably like arcing over and going through the rest of the circuit. So I'm assuming that if 4 amps was flying through the circuit, that a lot of stuff is going to be dead. So what we'll do is, I've ordered another one of these. I'll plug it in and hopefully it just works fine. And if that's the case and I can get it working, then I'll do a follow-up video to this video in where I try and add some improvements to this. So what I'm thinking is, obviously, probably, maybe the right thing to do would be to disconnect or to cut off the LEDs and then add a jumper wire or something and figure out a way to use the LEDs externally, basically. So that might be one thing to do. Another thing to do would be to improve this input situation, because this is ridiculous. Like getting my alligator clips, for example, to connect onto there, and you can see like you got a whole bunch of gap and stuff like that. It's just horrible. It doesn't stay as well. Although this time it's actually, no, yeah, it doesn't. So yeah, improving the inputs, maybe putting one of those DC things that you screw down on, because I found that when I was using it, it kept on coming out, so that was annoying. Obviously adding the reverse voltage protection so that I don't fry the whole bloody thing again. I'd like to possibly change these resistors, the R5 and R4, maybe take them down to 10 ohms and see what kind of voltage we get. Maybe even add a variable resistor there so that we can control the brightness of the LEDs on the fly. That would be quite cool. So if you replace these with 2 variable resistors and then you just, or potentiometer, and you screwed it, that would be cool to change the brightness of the LEDs. I think I'd like to do that. And probably the last improvement I'd like to do is figure out a way to get the blue LEDs to work off of 9 volts. I'm not sure what that would entail. Yeah, because I'm not sure how I would get that to work on 9 volts, to be honest with you. Obviously, it states that it should work with 9 volts, as you can see there. Apparently, it should work with 9 volts, but it doesn't for whatever reason. And what comes to mind is changing some resistor values. Maybe reducing the R4 down to 10 ohms would do it. Maybe, because I don't know. Other than that, I can't think. Obviously, the diodes have no effect, because when they're forward biased, then they're basically a short circuit, so they have no effect. The transistors shouldn't really have any effect. I remember on the simulation there was some spikes on the output, so maybe a larger capacitor would do the job. I don't know. I really don't know. So, but it would be cool if I could figure that out, how to get this thing to work off of 9 volts. If you have any ideas, let me know. Leave a comment down below. And yeah, if you enjoyed this video, let me know. I mean, I'm hoping to do a lot more of these. For me, it's not really about the video. I don't really do this, for the videos. I'm doing it so that I can learn and get better. And I must say, I'm probably about 5 or 6 hours into this whole circuit, in terms of the soldering and the research. So about 5-6 hours, and it's 5-6 hours well worth it to me. I also spent today about 6 hours studying for my communications exam, which I've got coming up, and I've learned practically nothing in those 6 hours, like next to nothing, literally. And for 6 hours of this, I've learned a bunch. So yeah, well worth it to me. And I'm going to be doing some more circuits. Like I said, I got a lot more kind of juicy circuits here, which I just really would like to figure out what's going on with all of them. So actually, I realized I might even have a spare CD 4017. Anyways, I'll see you guys in the next one. Take care. Let me know if you enjoyed the video. Leave a like. See you later.